Hi folks, this is Double Wings. Today I'd like to talk about quantum mechanics. Yes, quantum mechanics. So after you listen to this talk, you become really smart and you can brag to other people. You'll be very impressive. At least I'll be impressed. Now, what is quantum mechanics? What do you need to know about it? There are basically three basic laws in quantum mechanics. Of course, there are many other laws and theories and even hypotheses, but these are three basic laws. You have to remember. Number one law, Heisenberg's uncertainty principle, which basically says you cannot measure a particle accurately, or at least you cannot measure its momentum and its position accurately at the same time. So originally this was only restricted to the microscopic world. The reasoning behind it is, once you start to make observation of these tiny particles, let's say an electron, a photon, or even a proton, you need some sort of input into the system. And because the particles you're observing are so small to begin with, even if you shine a photon on it, a photon is pretty much the smallest particle you can get in the world. Its by definition is massless, which means it has no weight. And by theory, it also has the lowest energy. Even if you have a photon hitting this particle you're observing, it'll make this particle that you're trying to observe shift its position or change its momentum, or both. There's no way you can accurately get these data. If you find this hard to understand, I use a real-world example to illustrate this point. Let's say we cut two 2x4s. And we know to make a stud we need 8 feet. So we cut 8 feet. But there's no way you can be 100% certain that the two pieces of 2x4 will be exactly the same length. Even if the same person used the same machine to cut it, they will still not be the same. The reason is this: the moment your blade is touching the wood, the space around this action, the particles surrounding this action, is never going to be the same. In other words, at the time you're cutting the first piece of wood, comparing to the time you're cutting the second piece of wood, the particles around the blade will be different. So that would affect the actual cutting. Be as small as it will be, it is still going to be very, very tiny differences. Differences that you probably cannot observe even by very advanced technology. But if the apparatus gets precise enough, or getting infinitely precise, you will be able to detect the difference in the length of these two pieces of 2x4s. Okay, you say the particles around the blade will be different when you're cutting two different pieces, two separate pieces, 2x4s. How about let's put this cutting process in a vacuum. So there are no particles around the blade. Then you should have the two exactly same piece of wood, right? Same length. No. Because this time, when your blade is touching the wood, the temperature of the blade might be slightly different. You say, okay, let's make sure the temperature of the blade is the same. Here's the problem. How can you make sure the temperature will be exact the same? You cannot even get the same length on two pieces of wood. How are you going to be able to gauge the blade to be exactly the same temperature in two separate instances? So you see, in the real world, every action we take is affected by myriads of factors. Lots of them are microscopic. They're so small that we cannot observe. And the results of that, the differences are so small that we cannot observe. We just simply don't care, really. Because two studs 1 millimeter apart, not going to make a difference. But if you want to be exact, if you want to be scientific, these two pieces of wood will never be the same length. Okay, that's the first principle. Heisenberg's uncertainty principle. The second principle of quantum mechanics is particle wave dualism. People who have studied physics probably have seen this experiment that you pass a particle through two slits, and theoretically those particles, if you consider them as little balls, when they pass the two slits, if you have a screen behind the slits, you should have two lines of hits, or when the ball hits the screen, it makes a mark. Theoretically, you should have two lines of marks, right? So that's exactly what happens. Only when you're watching. The weird thing is, when you're not observing, if you shoot a particle, let's say an electron or a photon, it forms a wave. The results on the screen is a pattern of dark and light strips. It's not just two strips, which basically says this particle actually behaves like a wave. We know when you push a water wave through two slits, this actually would be best described with some graphs. But just trust me, a particle will exhibit both wave-like and particle-like properties. Now, first, scientists experimented with only small particles, and they thought it only applied to microscopic world. But since then, they have increased the size of the particles from a photon to electron to atom, from atom to a molecule. They still get this pattern. So, is it true that in theory every object is both a particle and a wave? Even macroscopic objects like a lamp or my body. Is my body a wave? Food for thought. A third principle of quantum mechanics is quantum entanglement, which is really very fascinating. It basically says in the quantum world you can have two particles. They are entangled with each other. When they are entangled as one, you don't know their exact property, or they exhibit neutral property. But should one of them, let's say magnetic wise, should one of them turn out to be positive, the other one will instantly become negative. Now this property actually has great applications in the real world. Since this change is instant, we know computers run on a binary system. It's basically 1 0 1 0. To produce these 1 zeros, there's always going to be a time lag. But with quantum particles, let's assume 1 is positive, 0 is negative. The turning of positive and negative is instant. So that would make computing vastly faster than the current system. So this one actually has great promises in real-world applications. And the fascinating thing about this quantum entanglement is that these two particles that's in quantum entanglement, they don't necessarily have to be in close proximity. They can be as far away as the universe, one on the one side of the universe, one on the other side of the universe. And as long as they have this entanglement, if one turns positive, the other one is going to instantly turn negative on the other side of the universe. Which means there's some kind of a transmission mechanism that's vastly faster than the speed of light, which we know is theoretically the highest speed one can achieve in the universe. I haven't been able to dig out any explanation for this, but it's just a fascinating phenomenon. So here are 3 basic principles of quantum mechanics, and if you want to really sound smart to your friends, you can try to digest these 3 concepts, and who knows, you may be able to show off to someone you want to impress. So number 1, Heisenberg's uncertainty principle. Number 2, particle wave dualism. And number 3, quantum entanglement. Thanks for listening. Bye.